These people are meteorologists. Not all. Some of them are on there for pretty. Some of them are on there because of practice. But you don't have meteorologists to do the program. But it helps if you don't, if you know some stuff. Oh, well.
Good evening, everyone. I'd like to welcome you to our monthly meeting. This is the Royal Astronomical Society of Canada. I'm Chris Pearce, the Centre President. And Happy New Year to everyone. Hope everybody had an enjoyable holiday season and raring to go for another year of meetings and learning new things. So on our meeting tonight, we have our normal agenda. So for those people who are new or visitors, we'll have some announcements first, and then we'll have our guest speaker. And then if you wish, after the guest speaker, there will be, we have a coffee, cookies, and tea in the 4th floor lounge of the Elliott building, which is, I always get it wrong, so that way. Somewhere over there somewhere. Or that way, maybe. That way. And up on the top floor. Rather than belaboring this, let's get into the announcements. So just to say a few things there. So our membership is currently 260, and there are 10 people whose memberships have expired in the past 2 months. So we're still holding our own. If anybody is a visitor here tonight, we have some complimentary copies of the Sky News magazine. This does come with membership, but if you'd like to pick up a copy, please do. I think that's about all I have to say. Reg, do you have a...
The January 2018 edition of Sky News comes with a health warning. It is full of eye candy. And so if astronomers read it, they might come out with hypoglycemia. So watch that. It's all about planetary nebula, and they're some of the most beautiful things in the universe. So if you haven't checked it out, do so. I've got a limited number of hard copies if you so wish. Come and see me after the meeting. Thank you.
Well done, Rick.
Thank you. Deb. So we have a special presentation from our second vice president.
Yeah. It's become a trend, we've noticed in this century, that people are becoming first-time grandparents.
And you know who you are, Reg.
It's not mandatory. Yeah.
His name is Andrew. He was born on St. Andrews.
You're welcome.
Wow.
Congratulations, Reg.
It's not for you.
Hold on. Oh, wow. Look at this. Oh, Thank you so much. I should say that he's very advanced. We've already got him an astronomy textbook called Goodnight Moon. So thank you very much.
Great. Treasurer Bruce.
Our current member account stands at $6,526, gaming at $20. I just got our first email to tell you all about the great paperwork I get to do the rest of the month. So that's nice. So I can get that and the stuff going on to the CRAs before soon. Checks are going out, paperwork is being done, and we have calendars. For those of you who didn't get any calendars, there's more.
Lori
$15 each. I wouldn't take it personally if you buy them from Lori instead of me, but
You got to keep the treasurer happy.
And we're looking at the Star Party. Both myself and Deborah are looking for new Star Party locations. We've knocked off a couple names off the list of Rod and Gun Clubs, seeing more interest in shotguns than us. And even though there was a space where we could have easily gotten in there, they didn't seem that interested. And we're looking at a lot of places in North Saanich right now. There was some thought about going to provincial campgrounds, but unfortunately the way the reservation system is being handled and the bots being used by private tour companies, we were basically going in there and buying up campgrounds and then reselling the campground use to European and Asian tourists. It's not really something you want to bet on, so I'm not going to do that. That's pretty much it.
Okay, thanks, Bruce. Ken.
Hello, I'm Ken. I'm the outreach coordinator. I've been told about an event on January 27th. Do you know what day that is?
So it's a Saturday?
Saturday, January 27th. Something here at the university. We meet here at 3 o'clock for solar viewing. If you want to participate in an outreach event for Bring Your Solar Telescope, I'd appreciate it. Possible Zoom doing as well. Is it university, Chris?
Yeah. Sorry. So Bruce is going to coordinate on our behalf. So it's the launch event for the RASC 150 celebrations. So the basic concept is as 3 o'clock arrives at each center, they will join a Google Hangout online and do whatever can be done at their locale. Hopefully some solar viewing, and there's, I think, a fullish moon that night. Knowing that it's January here, who knows? But as the time progresses across the country, other centers will join in. And so we'll be able to see what other centers are doing across the country, and other people will be able to go to this site. It won't be just restricted to people here at UVic or wherever they are. So it's an open website, I believe.
So that's
More
from 3 to
details.
5 p.m.
Roughly, yeah. Yeah, set up for 2 probably. So.
Okay.
And we thought we'd use the roof here if we do solar viewing.
I can always use your old magazines or astronomy books. I get out at outreach events through the summer. So if you're cleaning up and have extra magazines or books, please donate them to me. Thank you.
Thanks, Ken. Sid. School is back in swing.
Yep, we are starting another round of school visits. It's starting on Tuesday, I think, at Willows. And we had a good season before Christmas, and nice to see 2 weeks of respite during the Christmas time. So we are back on the bandwagon again.
Yeah. Thank you. Okay, inviting Canadians to explore their skies. Jim and Lori, I don't know if you want to come down here or not. Let's see if that works. Is that sort of?
Yeah, that's fine. That's good. Okay. Well, I have the shirt on. Welcome to the 150th anniversary of the RASC for all of 2018. And as as Ken and Bruce said, that the opening gambit is going to be right across the country, right, starting right in Halifax, and then we're just going to be going all the way across, trying to get as many centers. I think we've got probably something like 15 centers or something already kicking in, and we hope to get the Yukon. I'm not sure whether they're going to do that as well. And we'll be able at 3. It will be 8 o'clock their time, right? I think like in Nova Scotia, they'll be just kind of signing off, but we'll be able to see what happens, say in Ontario or in Manitoba or in Saskatchewan, and we'll be on, so that we'll be able to hang out with them and see what's going on. And there will be greetings from a variety of people right across, some notables across Canada, saying congratulations, and hopefully the 150th anniversary will go really well. Jim and I are part of the national committee that about 2 years ago, it seems
At
like
the
a little
London,
while, but came together to do some planning for what we wanted to do in 2018. And back then, it seemed like an awfully long time, to go. And now here it is. So it's amazing that we've got. So we are, Jim and I have been looking at trying to get together this Imagining the Skies contest, which is a photography plus add-on contest. And we wanted to show you a little bit about some of the things that we've been doing and getting ready for. And we'd really like you to be a part of this. And I think, Jim, I wasn't at the meeting last week, but Jim, you were, and I believe that it was the people asked. You want to just kind of tell them what we were going to do with this group?
This contest, which the leadership, the national leadership, had a very long list of ideas, and some kind of a photography contest was one of them. And Lori and I said at this meeting in London, it's a good idea, but there are so many contests. What can we do that will be different and effective? And so over the last 2 years, we've worked with the national group to come up with this idea. And the basic idea is to have this very simple contest between astrophotography or sketching at the eyepiece or creative works of art. And particularly to seek out newcomers. Try to get novices to go with you. I mean, all the experienced people who are regularly doing outreach, well, encourage novices to hold their iPhone up to the camera and submit a picture, or to do sketching, or to create a beautiful work of art and submit it to the contest. And so in this way, we think it's unique and very much to celebrate the 150 years of people getting acquainted with the night sky. Now, one aspect of this, and we've had wonderful support from Doug Renahan, who's a graduate student here at UVic, and actually can do IT-related things, which neither of us are very good at. And so he has really helped set up the contest. One key thing in the process of submission is, of course, to vet and make sure no inappropriate material gets posted. And for that, we're looking for a few people to work with us to volunteer to serve as veterans and to regularly, there would be some sort of a schedule. And on the days you've agreed to do it, you would check the website multiple times and approve any submission that meets the basic standards of decency. And so I think that's kind of it. Now, technically the website was ready on January the 1st. It's being displayed. However, none of the publicity has gone out about it, which is probably good. It turned out the national office, they had a slight communications issue they had to resolve, and that's now resolved. And so We think it's ready to go.
So we're trying to get, we are trying to get things onto Facebook and Twitter and on the national website. But just very quickly, maybe I just do this. So that's our splash page, our welcome page. That we just to say, you know, we want you to come in. We have two, just keep it there for a minute. There's two different contests going parallel to each other. One is the astrophotography and sketches at the eyepiece, and the other one is a creative works part. And so you can go in and you can decide which one you would like to do. So if you've made a quilt, or you've done a painting, or you've done something like that, you'd put yourself into the creative works. If you've done a sketch of the eyepiece, or you've taken a photograph, you would put yours up in the astrophotography part. When you go to the submit button, and you can do that, or you can just go to the astrophotography, go to the submit button. Then it goes up. You'll see up at the top. You can go in to see the gallery. The one that we're on here is the uploading of the photographs. There's rules, regulations, and what the prizes are. You can go into those set of rules, and then it's just simply giving you. So when you if you want to put something in, you're just going to simply put some of your basic details, your image details. We would like you to give a title to something. Just go on it just up a little bit. Talk a little bit about the description, maybe some of the vision of where you got it from. If you want to, you can put in things like camera models and that kind of stuff. And then the other thing it says right up in there is category. 3 different categories that people can put themselves in, because obviously I would not want to put in a photograph that is going to be directly competing with David Lee, or with Joe Carr, or with some of the other people sitting around here in this room, because I am not an experienced astrophotographer. And so we have made it so that you can become a novice, which is less than a year of experience, intermediate, so about 1 to 5, and then anybody with more than 5 years. You put yourself as an experienced astrophotographer, and you self-select that. And we're hoping that people will the correct category. We just have to be honest to be able to do that. And then you just simply go to your browser, and you're going to select the image that you want. You just simply put that in, and then it will come to a website that, as Jim said, it won't show up immediately on the website at all. It will come to us, and then we just have a very quick look, make sure that, as Jim said, it's an appropriate content. And then we just simply give it an okay, and it will go up on the website. It just takes an extra little bit of a layer before it gets up there, so it doesn't immediately go. Unfortunately, when you first go into it, it will ask you about things like checking off that you're 13 years of age or older, and that you've read the contest rules, and that you're not a robot. And it'll ask you to do a little bit of some CAPTCHA stuff, and we couldn't get away from that at all. So hopefully that will be all right for you guys. I know some of you feel that you might be robotic, but that's okay. And then the only other thing that we did have a bit of a problem with was, if there are children, and we do want children to put this in, is that we had to get this form that says that the parent is actually submitting the form for the child and saying that they are over 13, because we could not get that off the website. We couldn't get this thing saying, I confirm that I am at least 13 years of age. If you don't check that off, then you don't get any further on the website. So unfortunately, we had to kind of do a little bit of something. So once you've submitted the photograph, then it will go up on the gallery page, and then you'll be able to go and you'll be able to vote. Now, our problem is that, as Jim said, we're a little bit behind, and we actually haven't had anybody put any pictures up yet. And so we're really, really going to ask you guys, if you wouldn't mind, going home tonight, and every one of you in this room submitting a photograph of some kind. Taken in 2018. Oh, in 2018. That's the whole idea.
No pressure.
Right, no pressure. That's right.
Park the clouds.
The whole idea is that
Go
it has
home
to
and
be
paint
taken.
a picture.
So that's right. Do whatever you want.
Smile.
Diane, yeah. Because the whole idea is that we want you to do that
into
So then you can get to vote. So there is going to be there's a voting component. And we hope that you can. Now, what we have discovered is you can't vote for your own photograph. They won't let you do that. And B, you can only vote from your computer, your own, I guess, IP address. You can only vote for once for a photograph. So you can't go in and vote 50,000 times for the same photograph. So I mean, and that's kind of one of the things we're doing. So hopefully that will work. So we hope that we get this up, and that by the time we come back next month, that we have lots of photographs up online. We realize that the astrophotography is going to be the big one. The sketching, we really hope some people will put some things in over the year, and that the creative works might be a little bit longer in getting there. But just giving an idea that it's not, when you're observing and recording, it's not just astrophotography that you might do. We don't want to restrict it to just strictly astrophotography. We want to be able to have everybody do lots of different things. Yes?
Are there any prizes?
Well,
contests, prizes?
Yes, contest means prizes. We didn't want this to become like a big thing saying that you're going to get a great big $1,000 Meade telescope or something like that. We didn't want that, because a lot of people, we didn't want to end up having it be so that the people who would put a photograph in, just say photo of the week at Sky News, the Alan Dyer kind of things, would just simply win everything. So what we've done is divide it up so that the public votes will take some, and the images that gets the biggest votes over the year will get prizes, and then we will have a small jury at the end to kind of pick a few at the end. But each category will have one. So in fact, under the astrophotography, there will be novice, intermediate, and experienced. And under the creative works, there's also going to be 3 of those as well. So there's going to be quite a lot. So and
the sense is it's really public recognition of your work. But the anticipation is at the end of the year, the winners in all the categories will get a really nice plaque from the RASC, hopefully with their submission as part of it. So something really nice. But it's really to get people to get out and observe and bring others with them to get involved.
And we've been told that we'll probably be able to also publish the work in one of the publications, like the Sky News magazine or the Bulletin or the Journal or something like that. Yeah. So you'll get it actually published in the end. Yeah.
Or is there any limit to how current these pictures have to be? Can you go back into your archives and get one in, say, 5 or 6 years?
No.
No.
The observations have to be taken in 2018.
Oh.
That's the whole idea.
Get out in 2018 during the sesquicentennial.
So that's what we're trying to do. Okay, are there any other questions? Yes. Last day of submissions is December 31st, 2018. Like those, it's the entire year. And then we'll make a decision like very early in January we'll be able to kind of do that. So it's a year long project. So that's why Jim and I weren't totally, we're not frantic over it, kind of taking a little bit of a slow time to get going, because we're still changing things and manipulating content and stuff like that. So yeah.
Is there an option to take down, assuming that you've got all year and you want to get some up to get started?
Yes.
Arguably, some might be a really good one, which would be the level.
But
you want to knock the first one.
It's 10 per quarter.
Per quarter.
Yes, yeah, 10 per quarter, so that over 3 months you can put 10 up, and then in the next 3 months you can put another 10 up. So over the whole time you could put up a fair number of what, yeah.
So get working.
So get working. So thanks very much, everybody, and we will be in touch to have some people do some review.
And if anybody, should they contact you directly?
Yeah, either of us directly.
You'd like to help out as a monitor or a
I mean, something anybody can do that's got a computer at home, and if you're not able or feel comfortable doing the public outreach or all the other club activities, it's a way for people who can't get out to really help. We think we're pretty confident it'll be very straightforward and not time consuming. Although we would love to be flooded with images.
So,
That would be good.
Okay,
Yeah.
thank you very
Thank
much.
you both.
everybody.
Now, while I'm up front, I would just like to call your attention to the notice I put in Sky News about the Symphony Concert on the 20th and the 21st. It's the third concert grouping that the new music director, Christian Klucksen of the Victoria Symphony is doing. The two other groups of concerts he did last fall absolutely blew the audiences away. There is some magical rapport between him and the symphony. And for me, the highlight of the next concert on the 20th and 21st will be Host the Planets. And it's not only the symphony, but they're doing it jointly with the Greater Victoria Youth Orchestra, who are just amazing musicians. So, and there are two other pieces on the program, but as I said, if you want to, the winter blahs are getting you down, this will be a really fun concert. Talk it up to your friends and neighbors.
Thanks, Jim. Okay, national representative, Nelson.
Since my last report, the only thing that I've discerned that has happened has been some dialogue between the finance committee and the executive council that has to do with a dues increase. And the due increase, again, as near as I can tell, the dues increase that was proposed by the finance committee was $11.11. Which amounted to $1 per year since the last time the dues were increased. That was the law, it would be $11. And when that was posted, that precipitated 2 or 3 big long emails about how the membership was going to fall apart if such an increase was and so that's sort of where it stands. In fact, the last email I think I saw today was one of these emails that the membership will not tolerate this. And someone responded with an observation that one of the things complicating dues increase in the allocation of money within the RASC is that Canada Revenue has become much more wary of the interrelationship between money that is obtained by organizations that supports membership benefits, outreach programs, and the third and publications. So it's not easy and maybe impossible, as far as I know, for the RASC to use money that it gets from selling books to create a membership benefit, or money that is allocated for outreach has to be spent. So it's my assumption that this stuff about the dues increase will continue to sort of burble on and something to be resolved. At $10, $15. Any question?
If they actually allocated more than national to the centers, we'll use that for public outreach, no problem.
Yes. And members may have noticed there was a letter, I think, sent out to every member from the fundraising coordinator. Did everybody get one of those? I did earlier. Well, and I got a letter in the mail too. So maybe because I'm the president, I don't know. But anyways, there will be some, part of the strategic plan is to look for more sources of revenue because of these different streams within the organization. So funding the charitable part is the outreach. So membership needs to fund the member services, and then we have a business arm that has to be somewhat by itself. So that's basically, so it's a bit of restructuring, and so there'll be more forthcoming. But thank you, Nelson. Matt, anything from the technical committee? The telescope's in.
Telescope's installed. It's there for everyone to use. Please come up and use it.
Once we can see the sky again. Anything on the website front, Joe? Or
No report from the website. It's working along as usual. I did have one RASC Victoria Center calendar left. Like it for $12.
I ordered one.
Good. And there's your name on the.
Gone. And Michelle isn't here this evening. One thing that I'd like to bring to your attention is the Victoria Historical Society has a series of speakers on topics related to history of Victoria. And on the 25th of January, our own Dan Posey will be speaking on science, civic identity, and tourism at the Dominion Astrophysical Observatory. And so these take place, where is it? At the James Bay New Horizons on Menzies Street. And the doors open at 7:15, and their meeting starts at 7:45, and then the talk after, very similar format to ours. So if you're interested in that, it's, and what day of the week is that?
That's
25th?
Thursday.
Thursday, okay, Thursday the 25th of January. Great. And with that, there's some of the upcoming events, just to remind you. So we have the Victoria Centre Observatory evenings for active observers are on Saturday evenings, weather permitting. Michelle has arranged a Plaskett telescope session for next Friday, again, weather permitting. Astro Cafe does not require good weather, so that's on every Monday on the grounds of Sir James Douglas School. And we have the UVic Observatory on Friday evening this week. And again, the weather forecast is not looking particularly promising, but we will send a go, no-go email on Friday afternoon. The start time for that would likely be kind of 4 or 7 o'clock in the lobby just outside here, because we use the telescope on the roof. So, and that is that latter event there, the one here at UVic, is open to all members of the center. Are there any questions, or did I miss anything? Yes, I think, Rich, are we ready for?
Well, our guest speaker tonight, Patrick Hall, is setting up. I'll say a few words. In the dawn of time when I was at UVic, there was a lot of discussion about black holes, and some wit said that it's the perfect theory because no light can escape from a black hole. Nobody can prove that its existence. But tonight's talk is all about black holes that we can see, quasars. So Dr. Patrick Hall is on a sabbatical. He's normally at York University. He's been there since 2004. He actually hails from California, but both of his parents are Canadian, so he has a Canadian lineage. He went to Berkeley, had got his undergrad at Berkeley, and then he went to the Oasis of Astronomy in Tucson at Arizona University, and got his PhD there. He then went on to University of Toronto for a few years on an assignment, and then an assignment at Princeton as a postdoc. And it had the benefit that he also did some work in the Southern Hemisphere in Chile, at a number of telescopes down there, which is a great opportunity. And then he has moved on to the University of York University in northern Toronto. So I won't say any more. I'll let you take it away from here. Thanks very much, Patrick.
Thanks, George. Can you hear me okay? Excellent. So, yes, I'm going to talk to you today about black holes you can see. You note that is in quotation marks. So I'll explain that as we go along. If you have questions, I'm happy to answer them during the talk or at the end. Just raise your hand or speak up. So York wants us to use branding and have our York University picture up here, etc. But so I do that, but then I have the real slide to show, the real title slide to show what's really going on. This is, of course, an artist's impression, and we'll see some other artist's impressions that are a little more realistic later on. So what is a quasar? Well, it was in the 1940s that some astronomers first noticed that when you looked at the centers of some galaxies, the centers look different than most galaxies around. So some galaxies have very bright centers, where if you take a spectrum, there's some broad emission lines that were very puzzling when first detected. These are what we now call active galactic nuclei, or AGN for short. And fundamentally, the quasar is just a very luminous AGN, an AGN that puts out a lot of light. So here's a nice example. There's a galaxy, run-of-the-mill spiral galaxy. There's an AGN. So it's pretty obvious what the difference is. The underlying galaxy may be very similar. We think galaxies are affected by AGN, but the center sure looks different. And it was 55 years ago that Martin Schmidt first identified the first quasar. So these were objects that had broad emission lines, but at very puzzling wavelengths, until he finally realized that these were normal, well-known emission lines that just happened to be from a very distant object, and so the lines were shifted to unexpected wavelengths. And we still use that shifting today to measure how far away these quasars are. I'm not sure how many astronomers have made the cover of Time magazine. Maybe probably a few more, but it's certainly nice to see us up there from time to time. So quasar, I should say, is a made-up word, but I prefer to spend my life working on a made-up word than on an acronym. So I will say I work on quasars, not that I work on AGN, even though the difference may be a bit semantic. So that's great, but what causes a quasar? We have these luminous things at the centers of galaxies, great, but what causes them? Well, my colleague Gordon Richards liked to say a quasar is a process, not a thing. A quasar is what happens when gas spirals into a supermassive black hole at the center of a galaxy. And as gas spirals in, it forms an accretion disk, spiraling towards a black hole, and that disk launches an outflow. So for a long time, we thought of disks and outflows as being, different things, but now we really think that you can't, a black hole can't accrete matter without flinging some of the matter away in various ways that I'll talk about during this talk. But let's go even more fundamental. It's great that we think we know what quasars are, and I'll give you evidence to support my contention that a quasar is gas accreting into a black hole. But what is a black hole? Well, fundamentally, it's an object with an escape velocity greater than the speed of light. Because nothing can travel faster than the speed of light, nothing can escape a black hole. And general relativity predicts that stable black holes have mass, they have a spin, and they could have an electric charge, and that's it. There's no other quantities you need to fully describe a stable black hole. And a common misconception I clear up in my introductory astronomy classes is that black holes do suck in all matter around them. You can orbit a black hole just fine. If the sun turned into a black hole, we'd have lots of problems, but our orbit, the Earth's orbit, would not be one of them. The Earth would just continue orbiting around. But the closer you get to a black hole, the faster you need to move to stay in orbit. And if you get close enough to a black hole, no stable orbits exist. So if matter spirals into a black hole, it can stay in a circular orbit for a long time, but once it gets close enough, it's with nothing else to help it escape, it's going to fall into the black hole. And as we mentioned before, if you fall into a black hole's event horizon, because your orbit has become unstable, you will never escape. And if you have a black hole which is not spinning, this radius, this event horizon, is located at what's called the Schwarzschild radius. So the event horizon is just the region within which the escape velocity is greater than the speed of light. Carl Schwarzschild figured out that radius, and I was delayed showing this picture because I don't want you to be distracted by his mustache. So this escape velocity equation, I just realized that the shirt I wore, I'm practicing tonight, my NASA souvenir shirt with escape velocity, can be used with the massive black hole to
figure out the Schwarzschild radius. So it's a very simple equation that, and the key point that for us tonight is that as the mass of a black hole increases, the radius of the Schwarzschild radius increases. So more massive black holes are bigger. And we have some fundamental constants in here, but that's the key point. More massive black holes are bigger. So what the slide says, why does that make black holes a bit strange? Well, for the sun, or I should say for the mass of the sun, the Schwarzschild radius, if the sun became a black hole, would be 3 kilometers. So black holes 6 kilometers across form from the mass of the sun. But the most massive black holes, like the ones in quasars that I study, are 1 billion times the mass of the sun. It sounds like a lot, and it is, but at the center of a galaxy, over 14 billion years that our universe has been around, it is easy, relatively easy, to get that much mass forming into a black hole. And for that massive black hole, the size is the distance of Uranus from the sun. So we have a black hole as big as our solar system, surrounded by a disk of matter. We'll come back to that. So the black holes have lots of interesting effects, including one called spaghettification. If you approach a black hole, and this is one of the ways they're strange, your size relative to the event horizon matters. If you get in your rocket and travel to a black hole with a mass similar to the sun's mass, you will not be able to approach very close to the event horizon because you'll be torn apart well before that. As you get close to the black hole, the gravity at your feet will be much greater than the gravity at your head, and you will be stretched out by tidal forces and actually compressed a little, hence turning into spaghetti. So this term was coined by a science journalist in the UK, but it's fairly accurate. If you approach the event horizon of a black hole with the sun's mass, you'll be pulled apart. But if you were able to take a spaceship to the black hole at the center of our galaxy, or a massive enough black hole, you could fly your spaceship across the event horizon, no problem. You wouldn't be able to get out again, but you can cross the event horizon with no problem. That's because if the black hole is the size of Uranus's orbit, then the gravity on your feet and the gravity on your head are the same. You're feeling this pull from the black hole, but you're not being pulled apart. So the title here, The Planck Dive, is a short story about scientists who clone themselves and fly into a black hole because they want to see what a black hole is like from the inside. They know they'll never be able to escape, which is why they clone themselves. But you know, you can, at least I can understand their scientific interest in what a black hole would be like from inside. Okay, so it's fun to think about black holes, and there's lots of other reasons to think about them that I won't go into in this talk. Black holes are fundamentally quantum mechanical objects, but we don't, in other words, in some way they might be able to think of them as one particle, but we don't understand how to do that. And so Stephen Hawking and other people like him work on that idea to try and understand general relativity, our theory of gravity, and quantum mechanics, our theory of how the universe works at the smallest scales, in one theory. So they're still working on it. And black holes provide some insight into that. But as far as astrophysics goes, we do think black holes matter. It used to be that black holes were just a bit of an esoteric subject, but now we think they matter. And that's because every massive galaxy we now know has a supermassive black hole at its center. So our galaxy, the Andromeda galaxy, M87, et cetera, all have massive black holes at their centers. Now, if we look at the black hole at the center of our galaxy, there's not a lot of matter falling into it right now. But it's got a mass of 4 million times the mass of the sun. So there must have been mass falling into it in the past in order to grow up to 4 million times the mass of the sun. The black holes are mostly not active now, but in the past they were. And during those growth phases of the black hole, we think there were powerful outflows that affected the formation of the surrounding galaxy. If you've heard of the Fermi Bubbles in our own Milky Way galaxy, that we think is evidence for outflows from the black hole at the center of our galaxy. I didn't have time, unfortunately, to add a slide which showing those Fermi bubbles, but you can look at it online. We As far as the center of our galaxy goes, that provides us with some of the best evidence for a black hole. I've been talking about black holes, but why do astronomers think they're real? Well, we can study the orbits of stars around an object at, as far as we can tell, the very center of our Milky Way, called Sagittarius A star. So Dr. Andrea Gesh from here at UCLA has done this, and has found that the mass of Sagittarius star is 4 million suns. So let's take a look at the little animation. This is an animation of the positions of stars orbiting Sagittarius star, which would be right at the center. You've seen it already, but it's worth seeing again. This is the date. Middle of 1995. I tested the other animation, but not this one. Let's see if it looks like it's trying. We'll let it reach the end and then see if we can do it. Yeah, okay. One more thing to try. See if it works on a small scale. Yeah. All right. Well, I'll have to come back to that later. Okay, so we'll show that animation, which you may have seen. That's a cartoon of the actual observation. They use this Keck telescope. Take an image of the center of our galaxy, come back next year, take another image. They've been doing this every year since 1995. They now have a very impressive movie of what the stars are doing, orbiting this massive object at the center of the black hole. Excuse me, at the center of our galaxy. And there's so much mass in such a small area that's so dim that the only reasonable thing we can think of is a black hole. In other words, if it's not a black hole, it's something even weirder. And we'd rather not have that, so we're pretty sure. So the other fact that leads us to think quasars matter in modern astronomy is that there's a tight relationship between black hole mass and galaxy mass. We look at our galaxy, 4 million times the mass of the sun. We look at M87, a much bigger galaxy, much more massive. It has a much more massive black hole at its center. And we were really surprised to learn that this relationship is as tight as it is. The more massive the galaxy, the more massive the black hole. And we think that that arises because galaxies and black holes grow up together. Way back, they start as a gas cloud, gravity pulls it together, stars start forming, and a black hole forms and accretes more and more matter. As more stars form, the black hole feeds off those stellar winds and leftover gas and grows bigger and bigger. Until eventually, this feedback, these winds from black holes, shut down star formation in the host galaxy. And these three astronomers here have simulated the fueling of quasars during the merger of two disk galaxies. So I'm going to show you a simulation they did of two disk galaxies coming together, and we'll see the gas in those galaxies. So Milky Way, galaxies like our own Milky Way have lots of gas that's forming stars. When galaxies collide, that gas can heat up, and outflows from the quasar can have a big effect on those galaxies. And this is the cautionary tale. Dr. DiMatteo, Dr. Springle maintain their web presences online and give you nice photos. The only photo I could find of Dr. Hernquist was this one. So again, be careful what you post online because you never know how long it's going to be up there. Okay, here are two disk galaxies. We're seeing the gas, not the stars. So you got to imagine there's lots of stars here. You can find the stellar animation online, but I just want to show the gas one, if I can. Oh, it was working earlier. All right. Well, this is, I want to make sure to test my animations before I start. I'm just going to try one thing. The only thing I changed, change it back, and see what happens. All right, well, it's always something new. Like I said, last time I gave a talk, I brought a backup presentation on USB, and I brought a backup of my backup, and that was good because I needed the backup of my backup. but sorry about that. I did test it, and something has changed in the last half hour, and it no longer works. All right. If we have time at the end, I'll see if I can show these online, but the animation, all that it really fundamentally shows is that as two galaxies collide, their gas heats up. And that gas also gets driven to the center of the galaxy. And fueling the black hole, if you feed the black hole too much, it will start acting like a blender with the lid off and spewing matter back out into space. And that matter travels at very high speeds and basically blows out all the gas in the galaxy. So we now think that as galaxies merge, they sort of overfeed their black hole. The black hole blows out all the gas in the galaxy, and that's it for star formation in that galaxy. You end up with an elliptical galaxy. So two spiral galaxies merging, we think, produce elliptical galaxies where star formation gets shut down very quickly. Okay, so let's talk a little more about orbiting black holes. We've talked about the closer you get to a black hole, the faster you need to move to stay in orbit. If you get too close, there's no stable orbit left. What this means is that if you have a cloud of matter approaching a black hole, like the one in the center of our galaxy, that cloud will be torn apart, and it will end up forming a flattened accretion disk. Any cloud coming in will be coming in a certain direction. You can imagine it getting torn apart and ending up spiraling around the black hole in that direction. So a quasar is just a black hole plus accretion disk, plus more that I'll show in the next slide. But fundamentally, a black hole and accretion disk. We can't see the black hole directly, but we can see the accretion disk. In fact, if you think about it, a black hole is the size, a massive one, is the size of Uranus's orbit, surrounded by an accretion disk, bigger than our solar system, and hotter than the surface of the sun. So how can we see quasars? Why can we see quasars all the way out to the edge of the universe? Because they're disks of matter bigger than our solar system and hotter than the surface of the sun. That's a huge amount of light. And as literally as far as we can see in our observable universe, we can see quasars. And over the 55 years we've been studying quasars, we've come up with this picture. Now, this isn't the greatest picture, but it has a lot, it has all the components, so it's the one I use. We think we have a black hole and an accretion disk, gas spinning around. Farther out, there's a torus. I'm not sure exactly what this is, but we're pretty sure it's there. And coming out this accretion disk, gas clouds being flung away, and then relativistic jets, which I won't talk about in my tour because I don't work on them, but they do make for some lovely pictures, such as M87 here. This is M87 with HST. There's the center of the galaxy, black hole down here, and this is matter flowing out in a relativistic jet. So it's a thin stream of matter flowing out at nearly the speed of light. It has to do with magnetic fields. It's complicated. We don't understand all the details, but they make for some lovely photos. So quasars have a black hole surrounded by an accretion disk. Very often polar jets, like this one, two jets coming out in opposite directions, a torus of some sort, and outflowing gas clouds. Those gas clouds are the ones that shut down star formation in galaxies, and they're the focus of much of my research. We'll talk some more about them later. But first, I want to have a little interlude, since we're talking about black holes and accretion disks. What would they look like if we could see them up close? Well, gravity distorts the space around a mass. So if you could find yourself in a universe with no matter, or let's take Star Trek. Something happens to the Enterprise. It finds itself in a universe where it's the only matter. Well, if it fires its engines, it's going to go in one direction. It will never deviate from that straight line because there's no other matter to deviate its course. But in our everyday universe, matter that would normally travel in a straight line, if it finds itself near an object like the Earth, its path will curve. For example, go into orbit around the Earth. So gravity distorts space and tells mass how to move. So this applies even to light. Gravitational lenses, which you may have had a talk on or may have seen online. They make some lovely images. These are distant objects whose light is bent by gravity so that we see more than one image. So the strong gravity of a black hole means that the image we could see of an accretion disk, if we could get close to a black hole, is distorted by the black hole's gravity. Especially, it turns out, if the black hole is spinning. And the movie Interstellar from a few years ago shows this distortion rather accurately. So this is the accretion disk around the black hole in Interstellar. So how is this doesn't quite look like a disk? Why does it look like that? To show that. This is an accretion disk seen nearly face on, including the effects of gravity distorting the light from the disk. So we have this disk here, checkerboard pattern, just so you can recognize it. And you can see it's might be a little distorted, but it's pretty recognizable. There's also this in here, which is an image of the underside of the disk, which is a little hard to understand there, but it's actually easier to understand when you see things near the edge of it. Same top side of the disk. Between us and the black hole, the light from the disk just leaves, travels to us, no problem. The black hole, right here, the light comes towards the black hole, gets bent by gravity, and ends up over here. Right? Ends up coming to us from this direction. So it's light that would head towards it. It's light heading up from the disk that gets bent by the gravity of the black hole and ends up in our telescope. And this is an image of the bottom half of the disk. Half of the disk, so this is the top part of the disk, there's the bottom part right there. So this is a gravitational mirage, a gravitational lens of the accretion disk. And because spinning black holes are predicted by general relativity to literally drag space-time with them, a spinning black hole, if you can make a checkerboard pattern, would look something like this. The space is actually spinning around this fast spinning black hole. And if you can see that edge on, it looks pretty much the same as this, or at least very close, but you can see there is some distortion. A little bit of distortion, and in Interstellar, the disk shows the same distortion. So Kip Thorne, a professor at Caltech, was advisor in the movie Interstellar. He worked with the company making the special effects to make sure they used the right equations for how light would propagate near a black hole, and they did a pretty good job. This is pretty much what we think an accretion disk would look like if we could get up close and image it in great detail. We don't have the technology to do that yet, and won't for the foreseeable future. It's certainly lovely to see accurate images in Hollywood, for a change. So, we can't get pictures that good anytime soon. But we still think that we can image a black hole in the near future. If you want to image a black hole, you can't look at the black hole directly. It doesn't give off any light. But what we realize is we can look at the bright matter around it. I go to a telescope, I use an optical camera, and I'm looking at light that the quasar emitted in the optical, or maybe the ultraviolet if it's really far away. But in our own Milky Way, we can't see optical light from anywhere around the black hole because of all the dust between us and the center of our galaxy. At infrared and radio wavelengths. Those wavelengths can pierce the dust between us and our galaxy. And in order to get high resolution at radio wavelengths, we don't want to use one radio telescope in one location on Earth. We want to use radio telescopes scattered all over the Earth, tuned, pointing at the same spot and recording the time from atomic clocks very accurately, so we can combine the light from those telescopes as if they were a telescope as big as the Earth. That's what's being done by the Event Horizon Telescope. It's trying to test Einstein's theories with shadows of black holes. Now, it's a very busy slide, but the reason I'm talking about this is that you should stay tuned for results of the telescope in 2018. We expect that they'll announce even better observations than they've announced before. Whether they actually see the shadow of a black hole, we're not sure, but they'll definitely have some best images yet of the center of our galaxy. So here's the Event Horizon Telescope. Telescopes all the way from Greenland to the South Pole. All, well, not the Greenland one, but many of them looking at the center of our galaxy. Looking at M87, which has a bigger black hole, so that even though it's farther away, we still think they'll be able to see a shadow. And what the shadow of a black hole is predicted is that in the center of our galaxy, we don't think that there's much of an accretion disk. There's very little matter flowing into the black hole. So we just think it's sort of a hot fog around the black hole. Nonetheless, if you have this sort of fog around the black hole will block light, will bend light from behind the black hole and leave a gap, and we can predict what general relativity predicts, or we can simulate what general relativity predicts. General relativity says a black hole's shadow will be circular, depending on how fast it's spinning. But we're not 100% sure that general relativity is right. It's passed all the tests we've been able to subject it to, but this is a new test. And there are some predictions that say, well, maybe the black hole's shadow will be extended in one direction, and others, if it's spinning, let's say it's spinning around this axis, some theories say it'll be extended in that direction, others say it'll be extended in the opposite direction. But by measuring the shape of the shadow of a black hole, you can see that there are small differences here, and that's what the Event Horizon Telescope is doing. Seeing the shadow would be good evidence for a black hole. That would confirm our belief that this object at the center of our galaxy is a black hole, not something weirder, and might allow us to test general relativity in a way that hasn't been tested before. We're always searching for new tests. If it is right or not, it'll be very exciting to know. Okay, so we've talked a lot about black holes and the center of our galaxy in movies. Let's go back to quasars. So quasars are supermassive black holes surrounded by an accretion disk, and that accretion disk, as a matter of spiraling towards the black hole, is heating up through a kind of friction. As you move closer to the black hole, the gas or any object has to orbit faster to stay in orbit, has to move faster. So that means as gas gets towards the black hole, when it gets closer and closer, it's moving faster and faster, any collisions are more and more energetic. That means the gas heats up. Close to the black hole, the gas is emitting ultraviolet light. It's hotter than the surface of the sun. Farther away, it's emitting infrared light. It's cooler than the surface of the sun. And if you work out the numbers, black holes can emit as much light as 10 quadrillion suns. I think it's 10 to the 15. So a huge amount of light, because again, something bigger than our solar system, hotter than the surface of the sun, there's a lot of area in the solar system. Imagine the entire sky. Well, okay, imagine next time you see the sun during the day, imagine the entire sky covered that bright. That gives you an idea of what a quasar is. If you were that close to it, which you wouldn't want to be. Okay, so we believe there's an accretion disk, but with the wind flowing off it, but what would that look like in detail? Since it's the subject of my research, I'll talk about that in the last part of the talk. So here's some Canadian content here. Norm Murray at CETA and Dr. Sarah Gallagher Western. This idea. So this is a cross-section of an accretion disk around a black hole. There's a black hole. Here's the accretion disk. Close to the black hole, it's emitting ultraviolet light. Farther away, optical and infrared. And very close to the black hole, we think there's hot gas, which takes ultraviolet and optical light and gives it energy and produces X-rays. But this only happens very close to the black hole. We think that a wind accelerated from the black hole, accelerated from the accretion disk, forms what we call broad absorption line quasars. And I'll show a slide about them next. But a fairly generic property that if you have this accretion disk, the gas isn't just sitting there. The surface of the accretion disk is hot, gas likes to expand, so some of the gas gets kicked up off the accretion disk just by random chance, it sees a lot of light from close to the black hole. And so it's pushed outwards by radiation pressure. You may have heard about light sails. It's the same idea, that if you have a bright enough source of light, that light will actually push on the object around it. So we think the gas gets kicked up, accelerated outwards, and then falls back to the disk. Because X-rays will prevent this process from going on very long. So we think there's some gas here, which is basically just moving in circles, serving as a shield, and then beyond that, gas can be successfully accelerated out to speeds up to 20% of the speed of light. Or I suppose now these days I have to say 30% of the speed of light. Very fast winds. So how does this work? This simulation isn't going to work. Okay. So I was smart enough to remove this very large simulation very large animation from my talk. But there are astronomers who work with computers, not with telescopes. And two of them here, we saw them program. This is a simulation of what a wind from a quasar would look like. So here's the black hole and the accretion disk way down here. Wind off the accretion disk flows outward in two cones, two ice cream cones, waffle cones, back to back. And this resembles things that we actually see. Now we can't image a quasar with enough resolution to see it yet, but here's a red square nebula. It's a wind from an accretion disk of a different type in our own galaxy. And the same thing applies. We think down here there's a disk, and the wind is traveling off the disk in these two cones flowing out into space. So it seems to be, as I said, fairly generic process happening in a disk in our own galaxy on a very small scale, happening in disks around supermassive black holes all the way across the universe. When you have an accretion disk, some of the mass flows outward in these broad absorption line quasars. And that's what I do research on. And a few years ago, I came across in fact, on my last sabbatical, 7 years ago now, I found a type of object which no one had really predicted. So there was no warning of their arrival. So let's review. I'll show these objects in a moment. Let's give a little background. So matter spirals under a black hole. Ultraviolet light from small radii very close to the black hole pushes out any gas that happens to be kicked up off the accretion disk. So this hot accretion disk produces light at all wavelengths from infrared through optical. It produces a white light spectrum, but the gas tends to emit at certain wavelengths. And because the gas is whipping around the black hole, it produces very broad emission lines. The original way that AGN were identified through these broad emission lines. But that's not all, because about 1 in 4 quasars not only show emission, but they show absorption. So this is gas that's gotten between us and the quasar, and it's absorbing some of the light. So imagine a giant spotlight with wisps of gas passing across it and blocking some of the light. And as I said before, up to 20, these outflows can occur up to 20% of the speed of light. So here's a quick diagram of that. This is wavelengths of light from blue to red in the optical. Here's the spectrum of a typical quasar. It's a white light spectrum that's a little blue, so there's more light at blue wavelengths than red wavelengths. And it's got these broad emission lines that form a characteristic pattern we can use to measure how far away the quasar is. But a broad absorption line quasar has the same blue spectrum, same emission lines, but it also has absorption. This is gas that's flowing away from the quasar towards us and is absorbing some of the light before it can reach us. And in fact, some of these quasars, these BAL quasars, have dust associated with them, and they take this blue spectrum, absorb some of the light, and redden the rest, and you have this reddened spectrum showing lots of different absorption. But note that this is always blue shifted light. There's an emission line, and then at a bluer wavelength, there's absorption. Emission, absorption. So I think probably don't need to talk to this crowd about the Doppler shift, but it's such a nice animation, I'll leave it up there. The reason that this Doppler shift is useful is that we can use shifted wavelengths to measure the speeds of objects. So let's imagine we have a sodium lamp out in space, emitting yellow light. We have two other sodium lamps, one of them approaching us, like this over here, and the other traveling away. Well, this up and down motion plus motion away or towards us changes the wavelength of the light we receive. So motion towards us gives us a blue shift. Motion away from us gives us a red shift. So I discovered some BAL quasars which have redshifted absorption. So most of the time we see this luminous quasar and gas coming away from the accretion disk towards us, and we see a blue shift. But I found objects where instead we have this massive black hole and the gas is moving towards it. Which on the one hand doesn't sound too surprising, gravity of black hole, gas falling towards it, but it's a pretty rare phenomenon, we're still not quite sure how it happens. So this is another way of looking at the unabsorbed quasar spectrum. All you need to know is this is blue wavelengths, this is red, and here's the same spectrum I showed before, just in a different color now. Blue continuum with broad emission lines. And this was the object that I found one morning. It's, the wrong way Corrigan quasar. It has absorption, but the absorption is redshifted. The absorption appears to be moving away from us instead of towards us. So we have this nice picture of a disk with winds coming off of it, but somehow this quasar hasn't gotten the message and the gas is moving towards the black hole. Again, that may not be entirely surprising, but it's still a little hard to understand in the details. So the two things is no one predicted that gas falling in a black hole would look like this. Of course, the Kurosawa and Proga and collaborators and people who do simulations did predict that the black hole's gravity would pull gas in. No surprise, but it's actually hard to get the gas, to get cool gas falling in. Gas tends to heat up and then sort of fall back in. For gas at the temperatures we see, no one predicted. So it's still unexplained. This could be simply infalling gas, although the details are hard to understand. And if gas can simply fall into a black hole, why don't we see it more often? Why is it only 1 in 1,000 times? It could be that a rotating disk wind is to blame. We've talked about this disk matter spiraling into a black hole. That means that when a wind is launched from this disk, the wind is spinning. So here's a visualization I made of that. Black hole with lots of blue light at the center and cooler farther out. Let's imagine that this disk launches a wind. If that wind is launched at a very slow speed, the wind is mostly rotating. So these blue arrows show the rotation of the wind just above the disk, or if you like, the rotation of the wind of the disk itself. Blue shifted moving towards us over here, red shifted moving away over here. So if you have gas which is launched and is rotating like this, then you can see blue shifted absorption, and you can also see red shifted absorption. And that's what we see in some objects. We see both blue shifted and red shifted absorption. Sometimes we only see red shifted. Maybe that's infalling gas. Sometimes we see only blue shifted. That's pretty normal. So it's still up in the air. I have more observations of this that haven't really helped me resolve the puzzle. So I'm trying to think of new ways to test this. If I had to bet, I'd say it's probably some sort of rotating wind, but either way, it's something that's unexpected and sort of pushes the models to new places we didn't, new parameter space. So it allows us to test our models and improve them using these rare objects. So I've done something a little different in this talk than what I used to do, which is I talked a lot about our conclusions without telling you where the data came from that we make these conclusions. So, where do we get these ideas, from what data, and how do we check that they are correct? Well, a lot of what I've showed you, the spectra, anyway, come from the Sloan Digital Sky Survey in New Mexico. I've seen a picture of the Sloan telescope, but you may not have seen yet another Time magazine, not an astronomer this time, but a philanthropist, a businessman and then philanthropist. The Alfred P. Sloan Foundation has supported this survey of the entire sky using digital cameras for 17 years now. It surveyed 25% of the entire sky, 5 different wavelengths, spectrum more than 1 million galaxies and 500,000 quasars. Now it's in its phase 4, which includes something called the time domain spectroscopic survey, where we're in part going back to objects we know are quasars and getting another spectrum to see how they change over time. And it's revealing, again, unexpected things that that weren't predicted. So the Sloan telescope is very new and very efficient. Here it is. It does have a housing, but the housing is rolled off out of sight down to the left here. And what it does now is take spectra. So we know on the sky the positions of all the objects we want to get a spectrum of, but we're impatient. We don't want to get a spectrum of one at a time. So instead, we take a metal plate and drill holes in it at the locations corresponding to those positions on the sky, and then run fibers, optical fibers, from those holes to our spectrometers. Optical fibers are these things, which you may remember from the 1970s or 1980s. I'm pretty sure my uncle had this exact thing in his bachelor pad apartment, but optical fibers transmit light very efficiently. So this is the light down here. Seeing it come out the ends, we do the opposite, put the light in here, take it to our spectrographs. Very efficient, allows us to get 1,000 objects at a time, or 1,000 spectra at a time. And Sloan is a rather small telescope, but it can get 1,000 objects at a time, but it can't look at objects that are too faint. So we do need larger telescopes to look at fainter objects, or look at objects at higher time resolution. That's why we want to build a 30-meter telescope that Canada is a part of. But that's not all we want to do. We want to do big surveys of lots and lots of objects. TMT will be great for looking at faint objects, but it'll have a very narrow view of the sky. We'd also like to have a very wide view of the sky and get lots of objects. And that proposal is something that I'm involved with called the Mauna Kea Spectroscopic. So this is the proposed telescope. That will take spectra of over 4,000 objects simultaneously. Now, if you imagine this is a cube of telescopes, instead of building 4,000 telescopes, we're going to build one telescope to take 4,000 spectra. So it's very efficient. This would be an upgrade of the Canada-France-Hawaii telescope. The CFHT, Canada's been a partner for 40 years now. It's been a very productive telescope, but it's 4 meters and it's in diameter, and it's aging. But it's on possibly the best site on Mauna Kea. It's a site we'd like to keep. We'd like to have a bigger telescope there and run that telescope for another 40 years. So that's the proposal. And Canadian Astronomy thanks you for your past and future support. I've only mentioned here CFHT, TMT, our idea for rejuvenated TMT, but I haven't even mentioned Gemini, the Hubble Space Telescope, the James Webb Space Telescope, ALMA, et cetera, et cetera. We astronomers feel very fortunate to be able to investigate the universe on your behalf and then to come here and tell you about what we found. So in that spirit, thank you. And any questions? Please ask. Thank you.
Thank you very much for that fascinating talk, Patrick. Or anybody got some questions? Bruce?
I was wondering about with the early part of the talk about cosmology. Is anyone working under the premise that black holes came ready-made first? As I don't know, maybe fractions from a big bang?
So yes and no. Is anyone working on the theory that black holes came ready-made? Yes. Not exactly as you phrased it, but yes. So I said that I gave the common belief right now, our best guess is that black holes and galaxies grow up together. But there are some observations that are starting to suggest that maybe black holes grow up first. We're seeing some very massive black holes very early in the universe. And the longer that goes on, the more of those we find, it starts to become a little uncomfortable that you can have those black holes form so quickly. So people are now starting to think, well, actually starting to return some older ideas. maybe if a gas cloud of 1,000 times the mass of the sun can collapse directly to a black hole instead of forming a whole bunch of stars. So that's one thing, so sort of early growth of black holes. The other is what's called primordial black holes. In our early universe, there were lots of different particles created, and it's possible that some black holes could have been created. But the likelihood is they would have been very small and would have evaporated very quickly. So it doesn't seem to be the case that you could produce black holes right at the Big Bang. However, we haven't proved that that doesn't happen if you can modify theories of, if you modify particle physics theories in the right way, you might be able to produce that, make a prediction, we'll test it and see if it's right or not. So yeah, theorists are definitely thinking about it.
Is there any interaction with dark matter with black holes?
Probably. Our best guess is that dark matter is affected by gravity. In fact, that's why we think it exists. And so dark matter would be swallowed up by black holes just like warm matter. Because we don't understand exactly what dark matter is, we're not 100% sure of that, but you'll notice that black holes, as I mentioned, they have mass, charge, and spin. But they don't care if they were made of electrons and protons or electrons and positons. So electrons, protons, and dark matter, sure. It's an interesting question to then ask, well, how much of the mass of the black hole in the center of our galaxy started out as dark matter? Thank you for that, because that's a question I can ask my students when I go back to teaching next year. So yeah, we don't know, but we can estimate from theories, how much dark matter would be part of a black hole.
We had a picture earlier that had the cut across the cross section, and there was something. Was it called a torus?
Yes.
Could you talk a little bit about that?
Yes, and in fact, that's one of the reasons that I don't like that figure is it doesn't have our latest view of the torus. So in fact, sorry, it's a little farther back than I thought. Okay, so yes, this torus, the reason we think, so this is a dense torus, the reason we think it's there is that there are, sometimes when we look at a black hole, we see broad emission lines. Other times when we look, when we look at AGN, we see broad emission lines. Other times we don't see broad emission lines, we only see narrow ones. And we think that's because this dense torus blocks the light from the broad emission line. So what we now, our best guess for this torus though, is that it's part of the wind. So let me skip ahead a couple slides. Sure. Okay, so the point is that sometimes we can look at a quasar, let's pretend this is a quasar, sometimes we can see the X-rays and the broad emission line, the accretion disk directly. So we're looking at a quasar from this direction. But imagine that this wind here is opaque. Then if you look at it from this direction, it's still a quasar, but it doesn't look the same. And we think that this wind acts as a torus, or what we used to call the torus, we now call a dusty wind. And roughly half of quasars are hidden from us directly. There are other ways to figure out they're there, but we think this torus blocks roughly half the sky, as seen from, blocks the light from the quasar from escaping over about half the sky. So this torus was originally proposed to explain why sometimes you look at an object that you think has a massive black hole and you see broad lines, and other times you look at it and you don't. But again, we now think that the torus is better described as a wind. So I should probably use some of my sabbatical time to come up with a better figure than that on there that could show, to explain this a little more.
It goes around as almost like a cylinder.
Yes, well, as a donut.
Sorry.
Yes. But if I were to redraw this, I would link up this here and have this torus be another part of the min. If you come up afterwards, I'll see if I can find a better figure online to show you.
Sloan Digital Survey, you're taking new pictures and finding out new data. Can you give us an idea of what type of new data you're finding?
Yes, I can, but we're actually stopped taking pictures. We're only taking spectra now. There are other surveys that are doing that. Yeah. Well, part of the power of Sloan came from taking images and then taking spectra. But once you image all the sky seen from New Mexico, or at least all the sky away from the plane of the galaxy, it was time to move on and just focus on spectra. So for AGN, we're finding objects called changing look AGN, the objects that have these broad emission lines, and then you come back 5 years later and they don't anymore. Or quasars that look very bright, all this emission from the accretion disk, and 5 years later, it's much fainter. Over a long enough time scale, we expect that to happen, but these sort of 5-10 year time scales are sort of uncomfortably short for a disk to change as much as they seem to do. So maybe we're seeing some sort of unstable event where a disk sort of collapses much more quickly than we expected.
If our galaxy got excited and started using this, would that affect us here on Earth?
No, because there's enough dust and gas between us and the center of the Milky Way that it wouldn't have a direct effect. Sagittarius A star would look much brighter, so it might even show up at the optical, but there's a lot of dust there, and it would just be a dim object. So fortunately, we're shielded very, very efficiently.
Got a question?
There have been some suggestions that the speed of light goes to zero at the Schwarzschild radius. Can you comment on that?
There's different ways to think about the Schwarzschild radius, and there may be a coordinate system where that applies, but I don't think that's quite the right. It's not. I don't think it's conceptually the best way to think about it, even though you might be able to mathematically change the coordinates in a way that that's true. The reason is that if you imagine a Sputnik kind of thing falling towards the black hole, it's sending out pulses, radio pulses very fast. As it gets to the black hole, as it gets closer, those radio pulses get shifted to longer wavelength, and there's an increasing delay between them. But there comes a point where the Sputnik has crossed the black hole, and it may still be sending out pulses, but you won't receive any of them anymore. So that you can kind of see why you might say speed of light goes to zero, because it's emitting pulses, but you're not receiving them. And that would happen if the speed of light is zero. But a better way to think about it, I think, is that it's just inside the black hole. And the light may be traveling at the speed of light, but it can escape the black hole. And we don't exactly understand what happens inside the black hole. So if you start getting into the details of black holes, there's all sorts of interesting phenomena that can happen in different ways of looking at them. For my purposes, even for purposes of accretion around a black hole, unstable orbits and falling past the event horizon and stopping communication, those are really the basic things that you need to understand most of what we see in black holes. All the other stuff is sort of for Stephen Hawking and friends to quantum mechanics and GR. I wish them luck, but better them than me. I'm not going to get into that.
Okay, well, before we go on, I have one question. You talk about quasars as being very distant. What's the closest quasar?
So let me answer that two parts. First is, yes, quasars can be seen at very great distances, but quasars can be nearby. It's just that they were more common in the past. So the nearest quasar is either 3C273, preferred Cambridge radio source. Or there's another one called PHL 1811, which is very close to the galactic plane, which is why it wasn't discovered early on, but it's almost as close and almost as luminous as 3C 273. And I think closing this point, it turns out that of these two closest quasars, the PHL 1811 object, it's weird and we don't understand why. So that's 55 years of quasars, and it's still the case that some of the very nearest quasars are strange in ways that we can't figure out.
I think that's job security. The better the more complicated things are. At the back?
Yeah, just galaxies.
Yeah, so let me.
I missed that.
No, it's let me see if I can. I should be able to pull this out very quickly. Just have to remember the galaxy merger. So the reason is it really is worth seeing. Right. Taking a risk here. Is this the right simulation? No. I'm sorry, I don't want to be in a simulator. Okay, sorry. I learned enough. If I can't find it one search, I'm not going to find it. So what happens is that when two galaxies merge, they may start out with black holes at their centers. As the galaxies merge, they come together and gravity distorts them. That distortion ends up, that distortion and the dark matter surrounding the galaxies ends up pulling them together. So it's a kind of, not friction of stars actually running into each other, but the gas and the dark matter sort of coalesce. So these two black holes at the center of the galaxies will coalesce, and they'll end up most likely in orbit around each other. And if that's the only thing that happens, those two black holes can stay in orbit for a long time. They will merge because other galaxies and gas clouds will come in. So two black holes, if they far apart from each other, are stable for a very long time, billions of years. But two black holes with lots of stars orbiting around, gas clouds coming in, and maybe a smaller black hole from a smaller galaxy, that sort of dynamic environment ends up driving the black holes together. And one of the things we want to do with next generation gravity wave detectors is to look for mergers of supermassive black holes. So we have objects where we're pretty sure there's two massive black holes at the center of a galaxy because the galaxy started out as two different galaxies. And with enough of those in the universe, every so often, they're going to merge. And the only problem with doing that is that when they merge, they produce very long wavelength, very slow variations in gravity. So you would need to take a LIGO and put part of it in space, and then you'd be able to detect these things. So it's a long-term plan, but we now know that gravity waves are real, and so we're dusting off the plans for gravity wave detectors in space, hoping to see exactly how two supermassive black holes merge.
Okay, well, thank you so much for taking the time to share your expertise and passion with us. As a token of respect, we have a coveted calendar that has got photographs taken by many of the members from the Royal Astronomical Society. It's for 2018, and although the year is underway, there's still 97% left. Thank you again.